Hello, my name is Ernest Ryu. I'm an assistant professor of mathematics at UCLA. A few days ago, I visited UCSD under the invitation of Professor Yang Zheng to speak at the control theory seminar hosted by the ECE department. The talk is titled Optimization Algorithm Design via Electric Circuits. At the time, as I was addressing the ECE audience, I clarified that my area of expertise is optimization, and my understanding of electric circuits, circuit theory, and control theory is not that deep. And therefore, the things that I say in this talk that relate to control theory and circuit theory sound amateurish, and I ask for their understanding. At the same time, I also said that I was very happy to address this particular audience because this is a result in optimization algorithm design that utilizes insights and techniques that were originally developed for circuit theory and control theory. So let me start this talk by a high-level discussion of how one should design optimization algorithms. Now, granted, many of you who are listening to this talk may not actually be optimization experts. So you may have no experience designing optimization algorithms, and you may never have to design a novel optimization algorithm throughout your entire career. But many of you may have to design certain algorithms, not necessarily optimization algorithms, or you may have to produce new scientific discoveries, intellectual discoveries. So broaden the discussion to all of that. So the tried and tested approach to making algorithmic innovations is to just. So here, as I outlined in the slide, approach number one is to simply drink a lot of coffee and think very hard. And certainly this is the classic approach, and this is an approach that has worked very well because this kind of approach is responsible for most of the remarkable advancements that we appreciate in optimization and in many other fields. However, I want to pose a question, and the question is, can we build higher level tools to design and analyze optimization problems? Because I'm a mathematician, I'm an applied mathematician, and I like to think in abstractions. And the reason I do so is because I've observed that many branches of mathematics make progress through new tools or definitions that recontextualize the problem, recontextualize the original problem into a more abstract but tractable but easier form. So that's how a lot of progress is made in mathematics, and maybe that should be the same in optimization. So I'm interested in designing such tools in optimization that will help me do my work. So here's approach number two, and this approach starts to fit the bill. So this approach, which is called the performance estimation problem, is not the main focus of this talk. So I'll be very brief with this discussion, although the performance estimation problem does play a small part in towards the later part of this talk. The key insight of this approach is that the problem of finding a convergence proof for a given optimization problem is equivalent to finding a feasible point of a finite dimensional convex STP. And for the control theory audience, this is somewhat reminiscent of certifying Lyapunov stability for linear systems via STPs. So if you have a linear dynamical system, then the linear dynamical system is stable, Lyapunov stable, if and only if there exists a certain positive semi-definite matrix, and this matrix can be found computationally by solving a certain semi-definite program. So this performance estimation problem is an approach that elicits computer assistance in doing algorithm analysis in a way that is somewhat analogous to how we can use SDP solvers to certify Lyapunov stability. And this has been a very active area of research. I've written a few papers in this area, and this tool has allowed the discovery of efficient first-order methods and analyses in a computer-assisted manner. And here are some references. The first two references are the initial references that really kickstarted this performance estimation problem field, and this is one of the references of work that I've done. The next approach is called the scaled relative graphs. So again, I'll be very brief in the description of this because this is not at all a focus of this talk. I just want to tell you that this thing exists. So the key insight of this third approach to designing optimization algorithms and analyzing them is that the convergence rate optimization algorithm be viewed to be the contraction factor of fixed point iteration. The convergence rate of certain first order methods is given by certain geometric shapes on the 2D complex plane. So if you observe this set, so this is a lens-shaped set, and this corresponds to the action in a certain mathematical sense, the action of a certain operator. Namely, the operator is the Douglas-Rackhurst splitting or the ADMM operator, and we are assuming that the function is one of the two functions is strongly convex, and the other one is Lipschitz is co-coercive. So under those assumptions, then what we can show mathematically in a rigorous way is that the convergence rate of this algorithm is determined by the point farthest away from the origin. And in this particular illustration, you can see that, well, that point is the point A. This is the point within the lens-shaped set that is farthest away from the origin, and that length is given by the line segment, the length of the line segment OA. So now we can use some trigonometry, 2D Euclidean geometry, to do some Pythagorean theorems and all that, and figure out that the radius of this length OA has value that looks like this. Okay, so and here are the references that correspond to this line of work that tries to utilize geometric ideas, geometric techniques in the analysis of optimization algorithms. But today, I'm here to talk about ideas that utilize electric circuits. So this is the fourth approach. So the fourth approach is to use intuition from electric circuits. And the key insight is that many optimization algorithms can be identified with RLC circuits. Here, RLC means, for the non-control theory, non-circuit theory audience, RLC means resistor, inductor, and capacitors. So many optimization algorithms can be identified with RLC circuits composed with a nonlinear, incrementally passive resistor, gradient of F, and the equilibrium states of this circuit will correspond to primal dual solutions. So using this tool, we can design convergent optimization algorithms using circuit intuition. And I should clarify that in today's talk, what I'm going to propose is that we should use circuit theory intuition to think about and to maybe draw and write down certain circuits, and then have that intuition guide us in the design of optimization algorithms that will eventually be implemented on a digital circuit, on a CPU or a GPU. What I'm not proposing is to build physical circuits to solve optimization problems. The idea of building electrical circuits to solve optimization problems is a research area with a relatively long history. So you can there are ways to, let's say, use op amps, a lot of active components, to model hard constraints, and then try to build a circuit that solves a linear problem. This is certainly possible. It has been done many times. The main challenge of this line of work is that modern digital circuits are so hyper efficient that whenever you try to build an analog circuit that tries to match the performance of a corresponding digital circuit implementing a optimization algorithm, it's very, very difficult to beat the speed and efficiency of modern CPUs or even GPUs. In any case, building electrical circuits, that's not my line of research. That's not what I'm proposing to do. I don't have an opinion whether that's a good idea or a bad idea. What I am saying is a good idea is to use circuit intuition to design algorithms that we will eventually implement on digital circuits, on CPUs. So today's talk is based on this paper, which is joint work with my advisor, Stephen Boyd, and Tatiana Parshakova. Tatiana was a PhD student of Stephen Boyd at the time of doing this work. Now she has graduated, and she is now currently a postdoc at Yale. And then with myself and my PhD student, Jack Suh, who completed his PhD under my advisory, and he is now a postdoc at Rice working with Shiqian Ma. The paper is titled Optimization Algorithm Design via Electric Circuits and was published last December at NeurIPS as a spotlight paper. All right, so first, let's start with the sort of continuous time formulation. And let's start by stating the optimization problem that we will consider. Now, this is a mouthful, but it's important that we clarify optimization problem formulation. So let's spend the time, invest the time to fully understand what's going on here in the slide. So we will consider the optimization problem minimize f of x, but we will also impose a constraint on the decision variable x. So x is a length m vector. It is the optimization variable. It is a decision variable. The function f is a scalar value function. We allow for extended values, so the function can take infinity values. And the function is convex. So this is the main assumption that we make on the function f. Now, for mathematical reasons, we, in addition, need to assume that the function f is closed and proper. If you know what that is, if you come from an optimization background, if you know the convex analysis, that's good. If you don't know what that means, then that's fine. These are very minor assumptions, closedness and properness. These are minor assumptions made to just eliminate certain weird mathematically pathological cases. The main assumption, which is a pretty strong assumption, is that the function is convex. And then we're going to have the constraint that x is within the range of E transpose. So if x is in the range of E transpose, that is equivalent to saying that x is E transpose times z for some z. So in order for x to be within the range of E transpose, there must exist a z such that x is equal to E transpose z. And then E will be an n by m matrix. So m is a length n vector, and z is a length n vector. Okay, and next what we're going to do, but E is not an arbitrary matrix. E is a very structured matrix, and the matrix E arises from partitioning our variable into a set of nets. Okay, so the x variable will have components 1 up to m. And what we're going to do is we're going to partition these m coordinates, m components, into n partitions, n components, n groups. And we will refer to each group as a net, and we will have n nets, n1 up to nn. And then each row of E is going to correspond to one of the nets. A is going to be referred to as a selection matrix, and E will be defined in this way. So the values of E, so the ijth component of E will be +1 if a component j belongs to the net I, and then it will be 0 otherwise. So okay, so that's quite a bit. So what is the meaning of this? Well, what this constraint does, due to this particular construction, it enforces, so the constraint that x is within the range of E transpose, this enforces that two x values within the same group, within the same net, are constrained to be equal. So we are saying that certain components of x must be equal. This is the equality constraint that this constraint enforces. Okay, so now then we can if we invoke some standard convex analysis, we can show that, well, we can view this as a primal optimization problem, and then we'll derive the dual and then also write down the KKT system. And a primal dual solution corresponding to this primal problem and a corresponding dual problem will satisfy this relationship. So y will be within the subdifferential of f at x. And by the way, if you are unfamiliar with the notion of subgradients, what you can do is you can just simply cross this out and write y is equal to gradient of f of x and simply assume that the function is differentiable. So if you do not know what subgradients are, then that's fine. Just mentally, whenever you encounter this partial symbol within this talk, just mentally replace it with the gradient symbol. And then whenever we have the partial symbol, we're going to have this like set inclusion notation. But just don't worry about it. Just replace that with an equality. And there will be really no loss of information in terms of understanding what's going on. So the KKT conditions is y is equal to the gradient of f at x. X is within the range of E transpose, and then y is within the null space of E. Okay, so now I have to show you an example to make sure that that we are on the same page in terms of clarifying this notation. All right, so here's example number 1. So this is going to be a running example. So let the primal problem be f of x, but we minimize with respect to the variable x, which is a length 5 variable. And let's say we have these constraints, x1 is equal to x3, x2 is equal to x4, and x5 is unconstrained. Okay, so I've color-coded the constraints so that the variable x has 5 components, x1, x2, x3, x4, x5. And x1 and x3 are constrained to be equal, so they belong to the same net. So net 1 contains coordinates 1 and 3, and then net 2, the blue color, contains coordinate 2 and 4. And then x5 is unconstrained, so it just belongs to its own net. So net 5 just contains coordinate number 5. And all the components within the same net are constrained to be equal to each other. So this equality constraint, among the coordinates that belong to the same net, this can be represented in this way, or it can be represented under our standard form where we minimize f of x subject to x is equal to x is in the range of E transpose. And here, in this particular case, the E transpose matrix looks like this. All right, so here's yet another example. So we'll consider distributed optimization. And by the way, the formulation that I presented today is particularly useful at understanding distributed and decentralized optimization algorithms. So let's consider a setup where we have distributed optimization, and we have 3 computing nodes. And I'm going to label these nodes with alphabetical letters so that I don't want to get confused with the coordinate indices. So I'm going to say that we have node A, B, and C. So the 3 nodes, A, B, and C, individually have access to the function fa, fb, fc. And let's say we are minimizing it, we're solving a 2-dimensional optimization problem. So the optimization variable z is 2-dimensional. A standard approach in distributed and decentralized optimization is to take this optimization problem where the optimization variable z is shared, but the functions are individual. What you do is you decouple all the input variables. So in the original problem, we plug in the same z, but after the transformation into the function a, we plug in x1, x4, and the second one, x2, x5, x3, x6. So if you were to only look at this objective function, then you would think, well, the problem is completely now decoupled. There's no interaction between node A, node B, and node C. Well, the thing here, though, is that after all of this, we then enforce equality by saying that the first inputs, they all must be equal. So x1 is equal to x2 is equal to x3. We have this equality constraint. And then x4 must be equal to x5 must be equal to x6. So in this instance, we have 2 nets. We have the red net, which is net 1, and the blue net, which is net number 2. And the optimization variable x which has 6 components, well, the coordinates are decomposed into these 2 partitions. And again, we can express this optimization problem in our standard form with the matrix E transpose that looks like this. Okay, next, as our final example illustrating the notation, let's consider unconstrained optimization. So we'll consider the problem of minimizing f of x, where x is a length 4 vector. And here we have just no constraints. So when we have no constraints, we still can formulate this into our standard form. So our standard form is general enough to incorporate unconstrained optimization as well. How do we do that? Well, x is a vector of length 4. And all the variables are unconstrained. That means all 4 coordinates must each individually belong to its own net. So x1 belongs to net 1, x2 belongs to net 2, x3 belongs to net 3, and x4 belongs to net 4. Okay, but then under this setting, then what does this constraint look like? X belongs to the range of E transpose. That looks like there is a constraint, doesn't it? Well, here, the selection matrix E is just going to be simply the identity matrix. So X belonging to the range of the identity matrix is really it essentially becomes a null constraint, meaning that it doesn't really act as a bona fide constraint. It doesn't really constrain anything because any input vector X does lie within the range of the identity matrix. So really, yes, I mean, for the sake of consistency, we're writing down this constraint, but really there's no constraint here. Okay, so to review the notation, we are going to solve the optimization problem minimize of f of x, where x is within the range of E transpose. That's going to encode our equality constraints among coordinates that belong to the same partition. And we'll be partitioning the variable x which is a length m vector, into n nets. And our goal is to find a primal dual solution to this optimization problem. So we will find a primal solution x. At the same time, we'll find a dual solution y. And the primal dual solution will satisfy this KKT condition. Okay, so moving forward, how do we do that with circuits? Well, let's start with the notion of a static interconnect. The static interconnect is a set of wires, ideal wires, connecting m terminals and forming n nets. So, so think of this device and imagine that this is a 5-terminal device. And indeed, these are just wires. Well, what is the function of this static interconnect? So let's imagine we are going to connect this to another circuit component. Well, if we make this connection, well, what's going to happen is at this first terminal and at this third terminal, we have a wire directly connecting them. So the potential at this terminal and this terminal will become equal when you connect the static interconnect by the Kirchhoff's voltage law. And furthermore, because well, there are only 2 terminals here, the current here and the current here, they will add up to 0 by the Kirchhoff's current law, KCL. The same with here. So for terminal 2, terminal 4, this static interconnect will enforce that the voltages will be equal and that the currents will add up. And then for node number 3, there's going to be no constraint. It will not influence the voltage at this point at all, but it will ensure that the current going through this point, that current will have to be 0. So we'll denote with x the vector of terminal potential. So in this example, there are 5 terminal points. So x will be a length 5 vector, and it will just be a list of the terminal potentials that we can measure at these 5 points. And then we'll write y to denote the vector of currents leaving the terminals. So when we talk about currents, then it's important to designate a certain direction on the wire so that we can get the sign convention correct. So, so here are the arrows. So the currents leaving the terminals, that's the sign convention that we're going to go with. So again, x is the potential and y is the current. And this static interconnect will enforce Kirchhoff's voltage law, and it will enforce Kirchhoff's current law. Now, interestingly, the way we set up the selection matrix E is such that Kirchhoff's voltage law is actually equivalent to saying that x is within the range of E transpose. And Kirchhoff's current law is equivalent to saying that y is within the null space of E. So then, to put it differently, this static interconnect enforces the VI relationship that x must lie within the E range of E transpose and y must lie within the null space of E. The next device that we'll consider is a dynamic interconnect. So the dynamic interconnect is simply an RLC circuit. And this dynamic interconnect will have M terminals, as we did before, but it will also have access to a ground node. And it can be, otherwise, it's an arbitrary RLC circuit. So you're not allowed to put in any other active circuit components, so no op-amp, no transistors here, just RLC components. But you can wire them however you want, okay? So if you construct an arbitrary RLC circuit that is under our framework, it is a dynamic interconnect, but we're going to restrict our attention to certain dynamic interconnects, and namely the admissible ones. By admissibility. Well, if you have an RLC circuit, and when the RLC circuit, when your circuit reaches equilibrium, then meaning nothing is changing, everything is steady, then voltages across inductors will be 0, and currents through capacitors will also become 0. And the circuit theory language is that, well, people say that inductors become short circuits. So at equilibrium, inductors are basically just like wires, ideal wires. And then capacitors become open circuits. So capacitors become basically become disconnected. Okay, and we will say that a certain dynamic interconnect is admissible with respect to a certain static interconnect if the dynamic interconnect relaxes to the static interconnect at equilibrium. So, okay, so now let's take a look at this dynamic interconnect. And this one is actually admissible with respect to this static interconnect. Now, why so? Now, this, what I'm about to say, will require some intuition from circuit theory. But basically, at equilibrium, the inductor here will become a just ideal wire. So it will be a wire in parallel of the resistor makes the resistor irrelevant. And this just becomes just a pure wire connection. This one also becomes a pure wire connection. So node 1 and node 3 just becomes an ideal wire connection. And then moving on and proceeding, terminal 2 and terminal 4 just becomes it already has a pure wire connection. And then this capacitor and this capacitor gets disconnected. So, so if you then just remove the connections and just reorganize what it looks like, yes, it does become this static interconnect. So one way to see that a dynamic interconnect relaxes to the particular static interconnect and thereby becomes admissible, you can use this kind of circuit theory intuition, circuit theory arguments. Or another way to do this is you can do it in a more mathematical way. And via a linear system of equations. So mathematically, this admissibility condition basically boils down to this. So here within the circuit, we enforce that the voltages across the inductors and currents through capacitors are zero. And then so these are the possible current and voltage configurations. And we project that onto just the x, y voltages. And that becomes the VI relationship of the static interconnect. So this equation is the way to mathematically formalize the circuit theory intuition that I just demonstrated. So then what do we do with the interconnects? Of course, we're going to connect them to the gradient mapping of f, or the subdifferential operator of f. So what we'll do is we'll view gradient of f. Again, this is the subdifferential operator of f, but if you don't know subdifferential calculus, think of this as the gradient of f. So remember, f is a function that takes in x, which is a length n vector. So the gradient f is mathematically a mapping from a vector, a length n vector, to a length n vector, the gradient. So what we'll do is we'll view the gradient as an m-terminal electric device that is also grounded. And we will view x to be, and again, x is the length m vector. We'll view this as the potential at these m input terminals, excluding ground. And we'll view y to be the currents flowing into these m terminals. Okay, so then what the gradient operator does is, if we view it as an electric device, it enforces the VI relationship that the current y is equal to the gradient of f evaluated at x. So if you impose a certain a set of m potential values at the input terminals, that will induce a certain current, and that current is given by the gradient of f. So then what we'll do is we'll connect this m-terminal device to the interconnects. So we'll connect it to the static interconnect, and then we'll connect it to the dynamic interconnect, and then let's see what's going to happen. So in this picture, which we have already connected it to the static interconnect, we have a very nice immediate consequence. And that is that connecting the static interconnect to the gradient of f, it enforces the VI relationships. X comma y is in the range of E transpose and times the null space of E. That's enforced by the static interconnect. And we will have y is equal to the gradient of f. That is enforced by this block. So if we combine these two sets of conditions, we actually just get the optimality condition of the optimization problem that we had at hand. So to put it differently, let's imagine, and this is all in imaginary land, because again, I'm not saying we should build. Imagine there is this nonlinear resistor that corresponds to your convex function and corresponds to the gradient of your convex function f. What we do is we connect this nonlinear resistor to the static interconnect, and it will immediately equilibrate because these are just ideal wires. And then you can take your voltmeter and probe the potentials at all these 5 points. You write them down, and the voltages at these 5 points, that will be the solution, the primal solution to the optimization problem at hand. Okay, so this is very nice. But what has been accomplished? Well, actually not that much. So what we have done that the KKT condition of our convex optimization problem has the same form as sort of theory way of describing it. So we found this interesting correspondence, but nothing, we haven't discovered any new algorithms, nothing has been done yet. So really, the interesting thing happens when we connect our gradient operator with the dynamic interconnect. So when we make this connection, well, when we make this connection, which is also called composition in the language of circuit theory, when we compose the dynamic interconnect with the gradient of f, well, what happens is, because capacitors and inductors are stateful electric components, the circuit becomes dynamic in the sense that the voltages and the currents depend on time. And perhaps let me clarify the notation here. So the x, these are the voltages, these are the potentials at the M terminals, but there are many other sort of points where you can put a voltmeter and probe. So all these points, this point, this point, this point, this point, and this point, these voltage values are all encoded in the vector V, and the vector V also contains x. So V is the set of all potentials of interest within the circuit, and then x is a subset of those that are here. And the same with the currents I. So I is the current measurement at all the points in the circuit. Actually, I is the set of currents across all the electrical currents here, and also the currents exiting the dynamic interconnect. So I is a longer vector that contains a y as a subvector. Okay, so now we have a RLC circuit connected to this nonlinear incrementally passive resistor. And the equations that govern this imaginary circuit system is this. So this is the resistor equation. V is I R. So this DR notation, this is just a diagonal matrix containing all of the resistor values. So the circuit may contain many resistors, and we are not making the assumption that all the resistor values are different. The resistors can have different resistance values, and those resistance values are encoded here as a diagonal matrix, encoded in this diagonal matrix. The same with the inductor here. So DL, that's the diagonal matrix with all the inductance values, and then V is L times I dot. And then I is C times V dot. So this DC, that's again a diagonal matrix containing all the capacitance values. So these here we have the time derivatives. So that's the expression of the dynamic nature of the circuit. And then here this A matrix is the I'm trying to remember. It's the reduced node incidence matrix. And this one encodes Kirchhoff's current law. This one encodes Kirchhoff's voltage law. And this is the IV curve enforced by the relationship enforced gradient mapping of F. Okay, so we have this electrical system, this electrical circuit. Now, I'm a mathematician, so I wanted to spend a bit of time to understand whether the circuit is well-posed, because we're using our imagination. So it's perhaps not immediately obvious that this circuit is sort of mathematically well-posed, because so this thing is referred to, this thing is not a differential equation, because yes, we have derivatives here, but here we have equations that don't involve any derivatives. So usually this would be referred to as a differential algebraic equation rather than a differential equation. So it's a DAE, differential algebraic equation. But wait, it's not even an equation, because here we have a subdifferential operator and we have the subgradient inclusion. So this would actually be referred to as a differential algebraic inclusion. So, and it's a priori not obvious whether this would be a well-posed dynamics. So for the sake of a mathematical precision, we decided to show that this system is well-posed. So I'll sort of cover this theorem quickly. So we assume that F is strongly convex and smooth. This is just a set of assumptions to make things easier, and we believe this theorem should still be true even if we relax these assumptions. Convexity should be essential, but the strong convexity and smoothness I think it shouldn't be necessary. In any case, we need to impose initial conditions that are in a certain sense consistent with the circuit. And then in this case, then we will have a unique Lipschitz continuous curve satisfying the that describes the system that solves differential algebraic equation. So now in the sense of differential equations, this dynamics is well posed, so it's okay for us to study it mathematically. So now let's try to understand the dynamics of the system. So whenever you have a dynamical system, especially one that involves power and energy, an important question, a natural question to ask is this system stable? And the answer is yeah, this system is stable actually, because of energy dissipation. And the very short answer is this system is stable because this system has no active components. All the components, the RLC components, are components that do not generate energy. The resistor dissipates energy, and also the gradient mapping F, the gradient of F itself is viewed as a nonlinear resistor. It's a passive component that will only dissipate energy. Energy will be dissipative, and therefore we will have stability. Okay, so now let me make that argument a little bit more formal. All right, so let V star, I star, X star, Y star be a set of equilibrium values of voltages and currents. And let's assume we have we have an admissible dynamic interconnect composed with the gradient of F. Then the energy at time t, which we define here, is the voltage in the capacitor squared time plus the energy, the current in the inductor squared. So the energy stored in the capacitors, the energy stored in the inductors, that's the energy of the system. Because as we all know, resistors dissipate energy, but resistors do not store energy. Only capacitors and inductors do. Now, one thing that I want to note is that usually the energy stored in a capacitor is simply voltage squared. But here, instead of voltage squared, what we need to work with is voltage minus equilibrium voltage squared. So we will be squaring the deviation from the equilibrium, and we will refer to that as the energy, the quote energy in the capacitor. The same with the inductor as well. Instead of just the raw current squared, we will compute the deviation of the current from the equilibrium current and square that, and then we will refer to that as the energy stored in the inductor. In any case, we take the derivative of this, we do some analysis, and we get that the energy dissipated at any given moment is the power dissipated by resistors. By the way, I want to clarify this notation. So dr, that's again a diagonal matrix containing all the resistance values. So this is simply the sum of all the power dissipated by all the resistors, because there can be more than one resistor. So this is the sum of all the powers dissipated by all the resistors combined. So this is the power dissipated by the resistors, and this is the energy dissipated by the gradient mapping, which is, again, we view it as a nonlinear incrementally passive resistor. So these are all, energy is always dissipated, so the energy decreases as a function of time. So I've been saying this word incremental passivity for a while, and my understanding is that it's a somewhat it's a term from control theory, but I think it is a somewhat obscure terminology. So let me explain. So let's say you have a VI relationship. This VI relationship is said to be passive if, well, positive voltage induces positive current and negative voltage induces negative current, basically. So this is the condition that defines passivity. And this implies that the VI curve must go through the origin. So, and in particular, if you assert 0 volts across this particular component, then you will have 0 current. That's a key defining feature of the notion of passivity. But I've been saying that the gradient mapping is incrementally passive. It's not passive. So the incremental passivity definition, it looks like this. And basically, here's an illustration. So basically what this means is that the VI curve is a non-decreasing curve. It's an increasing curve. And it does not necessarily go through the origin. So the gradient mapping of F is incrementally passive due to convexity. And in the area field of optimization and convex analysis, this identity is referred to as monotonicity of the gradient mapping. So the gradient mapping is incrementally passive, but it's not necessarily passive. So in other words, if you assert 0 volts across the gradient mapping of F, you will not necessarily get a zero current. And because of this property, because gradient of F is not passive, the energy must be defined with the potential and current deviations rather than the absolute potential and currents. So basically, I'm skipping the description. I'm going through this argument quickly for the sake of going through things quickly. But what I'm saying is that the reason we need to subtract the equilibrium voltages and equilibrium currents is this is because gradient of F is incrementally passive. All right, so with all of that, now we have a convergence result. So the convergence states that, let's assume the gradient, the function F is convex, and furthermore strongly convex and smooth. And these assumptions, I believe, can be relaxed, but we did not bother. So in this case, if we assume, furthermore, that the dynamic interconnect is admissible with respect to the static interconnect, then we have convergence. So here we have our big circuit, and if we only look at the inputs, the voltage and the current at the terminals, then that converges to a primal dual solution. So yeah, so we have our RLC circuit, our admissible dynamic interconnect. We connect it with the gradient mapping, and initially it will do whatever. But we let it equilibrate, and once it equilibrates, we measure the voltages at all the terminals. That gives us our primal solution. And then somehow we measure the currents going through these terminals, and that gives us our dual solution. Okay, so next, let me show you how a lot of classical first-order optimization algorithms can be modeled with this circuit formulation. To do so, let me show you this sort of lemma involving the Moreau envelope. So let R be a positive resistance value or a positive regularization value. And let's say we have a function f, and let's assume it's convex. Then the Moreau envelope of the function f with parameter r is given by this. So the Moreau envelope uses this kind of weird notation where we have this kind of pre-superscript. So r pre-superscript r, this is the Moreau envelope. That's a function. And the function, the way you evaluate it is you take f of z plus 1 over 2r, z minus x, and then you minimize with respect to z. This is referred to as an infimo convolution. And a key property is that the Moreau envelope is more smooth than the original function. Now, interestingly, the Moreau envelope, which has a lot of uses in optimization theory and convex analysis, has a very nice correspondence when we think of it in circuits. So in circuits, if we have our gradient of f and we connect a resistor in serial, we connect this resistor in serial with the gradient mapping, that is equivalent to considering the gradient of the Moreau envelope. So when I say that these two circuits are equal, what I'm saying is that these two circuits impose the same VI relationship at the point at the pins of X. Okay, so perhaps, well, I'm skipping the gradient descent circuit because it's more simple. So one of the most famous algorithm is Nesterov acceleration. So let's try to understand what Nesterov acceleration looks like in circuits. Well, if you consider the classical Nesterov acceleration that is used when the function f is strongly convex, the circuit looks like this. Let's behold the circuit. So we have a capacitor, we have a resistor, we have an inductor, and then we have a negative resistor, which might initially be a little bit concerning. But just moving on, if we take this circuit the dynamics will be described by a certain differential equation. You can just write down the differential equation. And this is the differential equation corresponding to this circuit on the left. Okay, well, it's this thing. Now, what we'll do is we will choose the value of R, the resistor value R, to be root L over C, so that this term cancels out. And this R equals to root L over C. That you can understand that as a sort of a value corresponding to critical damping. So when you choose this R so that this component vanishes, and then set L to be some value, C to be some value, then we recover the classical Nesterov ODE, which, as we know, it achieves is commonly known that it achieves an accelerated rate. Now, going back to the negative resistances, at first sight, this might be concerning because, well, first of all, is this even physical? Well, I mean, I guess we were never insisting that anything be physical, so it's fine for us to imagine a negative resistance. But if you really wanted, then you can implement a negative resistor using an op-amp. So an op-amp is a certain active component that consumes power. So if you're willing to use active components, you can emulate a negative resistor. So I mean, it kind of is physical if you insist on making it. But okay, so putting that aside, is this circuit stable? Because now it looks like this circuit is no longer consists of only active components, right? Passive components. This minus R is an active component. It generates power. So maybe this circuit is not stable. Well, the way we can know that this is indeed stable, that it ought to be stable, is that because the function f is R smooth, we can sort of undo this gradient of f notation and pull out the resistance that is sort of here in serial. And now this negative resistor and this positive resistor, because they have the same resistance values, they just cancel out and become a pure wire. And once you cancel these two resistors out, then now you're only left with passive components. So then the circuit, because of energy dissipation, must necessarily be stable. Okay, now I'm going to move through these examples a little bit quickly, but I'll just mention that again, that this circuit framework is particularly useful at modeling and understanding distributed and decentralized optimization algorithms. And one of the most famous and widely used such algorithm is called decentralized ADMM. So in decentralized ADMM, we consider the setting where we have n computational nodes, and each node has access to its own function. But the computation happens on each individual node in each individual machine, if you will. And then the communication across these nodes, it happens on a certain network graph G. So within this network graph G, you have the n nodes as the nodes of the graph. And node I and node J are allowed to communicate if there's an edge between these two nodes. And for the simplicity, what we'll do is we'll just illustrate the study where node J and node L is connected. So if node J and node L is connected in this network graph, then the connection is going to be like this. So through this LR parallel circuit thing. Okay, so this circuit corresponds to decentralized ADMM. How do I know that? Because I can write down the dynamics of this circuit in this way. And then what I can do is I can just simply discretize this with a simple Euler discretization. And when I do so, I recover this algorithm on the right, and that's decentralized ADMM. Okay. Next, we have another decentralized optimization algorithm, and this one is called PG Extra. So PG Extra, again, considers a setting where there are n computational nodes, and each compute node has access to a function f, which is convex, and a function h, which is differentiable. And again, I'm going to go through this quickly, but there's a computation graph, and if there's a network graph, and if node L and node J is connected on this network graph, then in PG Extra, it's connected through this connection. Okay, and how do I know that? Well, I can stare at the circuit, and I can define this so-called mixing matrix W, use that W to help with my notation, and describe the continuous time dynamics, which looks like this. And then I just discretize, and I will get this thing, and this is a simple Euler discretization, and this algorithm is indeed a PG Extra. All right, so we have this continuous time formulation, and we've established a continuous time convergence result in that if we connect a admissible dynamic interconnect to our gradient of f, we will have convergence in continuous time. But that's actually not enough, is it? Because in the end, our goal is to design an algorithm that executes not in continuous time, but executes in discrete steps that can be an algorithm that can be implemented in a for loop on a digital computer. So, and this is an issue that has sort of troubled a lot of research in continuous time formulations of optimization. And that is that we started out with the consideration of an optimization algorithm as something that is already discrete time. Decentralized ADMM, gradient descent, Nesterov acceleration, PG extra, these are already a discrete time algorithm. And then we consider their continuous time limits. And that corresponds to a certain differential equation. In our case, we argue that corresponds to certain electric circuits. But these are continuous time objects, not implementable algorithms yet. So then the natural thing one might think is, well, let's just simply then take these circuits and discretize them. The problem of that is if you take a circuit or a continuous time dynamics, then do a naive discretization, that often doesn't work. That often does not preserve the convergence property of the continuous time system. And even though the continuous time system converges, as we have already established, that does not necessarily mean that the discretized algorithm converges. So how can we ensure that we find a discretization of this circuit that indeed converges? Well, what we're going to do is we're going to ensure that the discretization has what we call sufficient dissipativity. So what we'll do is we'll take these circuits and we'll consider a two-stage Runge-Kutta method. And the specifics of this RK is not that important. The point is that it's just some specified RK discretization. And in this Runge-Kutta discretization, we'll have parameters alpha, beta, and h. So it's a parameterized family of possible discretizations, two-stage Runge-Kutta. Then what we'll do is we'll consider the energies stored in the circuit at time t is equal to kh. So h is going to be our time discretization, and at time the discretized time t, this is the energy. Okay, so this is the same energy that we had considered in continuous time, and we just write it out for the discrete time energy. Now, we had established that the continuous time energy is dissipated, so we want that to happen with the discrete time energy as well. But we want to also ensure that it converges. So what we need is this sufficient dissipativity condition, which says that ek plus 1 minus ek, if that's less than or equal to 0, then that means it's dissipative. But we'll also require that furthermore, it's dissipated by this amount of slack. So this inner product is going to be positive by convexity, by incremental passivity of the gradient of f. And we will require that this holds with some positive, with some positive value of eta. And we show that if it's the case that our discretization satisfies this sufficient dissipativity condition, then the discrete time algorithm will converge, just as the continuous time dynamics converged to a primal solution. Okay, but we're not done yet, because how do we find then a discretization that satisfies this sufficient dissipativity condition? And well, we can actually do that in an automated way. So what we do is this automatic discretization that relies on solving what's called a performance estimation problem. So in the interest of time, I won't explain this optimization problem in detail, but what I'll just say is that we can solve this optimization problem. And if this optimization problem has a strictly positive objective value, then the discretization is not sufficiently dissipative. But if the optimal value becomes 0, then it does satisfy the sufficient dissipativity condition. So given a particular discretization, we can solve this optimization problem to check whether it is sufficiently dissipative and therefore leads to a convergent algorithm. And the way we can solve this optimization problem is there's a somewhat non-trivial a transformation that can turn this optimization problem into a convex finite dimensional semi-definite program. And this is borrowing ideas from the performance estimation problem. So given a discretization, we can check whether it's a good one. So let me conclude with an example. So here we have an example where if this is, I want to solve the unconstrained optimization problem where we minimize f of x. And I just constructed this whatever circuit. It's just some random circuit that I just put in. Okay, and now I want to construct a convergent algorithm out of this. So the way I do this is I need to specify some resistance and capacitance value. So I'm just going to say the resistance value is 1, capacitance is 10. And then we can use our automated discretization method. And when we do so, we get the sufficient dissipativity parameters, a positive value of eta with these discretization parameters. So h is 6.66, alpha 0, beta is 1. We just plug this into our formulation, and we now get a provably convergent algorithm. So this is a weird algorithm, but it's an algorithm. And according to our formulation, it is provably convergent. All right, so I'll conclude. So with our framework and circuit intuition, we can first, in the first step, design a continuous time dynamics, which is not yet an algorithm, but we can design a continuous time dynamics with a convergence guarantee via the energy dissipation. And so this is designing the circuit. And then the next step is we can discretize this continuous time circuit into an implementable discrete time algorithm using automatic discretization. And when we do so, we will ensure to preserve the convergence property. In continuous time, the convergence proof is that this energy dissipates, and therefore we have convergence. That's the proof outline. We will use the automatic discretization tool to be able to find, in an automated fashion, a discretization that preserves this convergence proof. So that is to say that it will ensure the sufficient dissipativity condition holds, and that will imply that the argument of energy dissipates and therefore converges, that argument will remain valid in the discretized algorithm as well. And finally, these are the sort of illustrations. These are the circuits that I had shown at the very first slide of this talk. And it outlines, it illustrates several different classical optimization algorithms, many decentralized optimization algorithms expressed as circuits. Okay, that's it for my talk. Thank you for your attention.